I'm going to present a small demonstration of the skyex package, which is an R package that solves the entity linkage process. It covers all three steps of this process, from blocking, pairwise comparison, labeling, and finally we offer an extra module for analysis and visualization. You can take the code for this package here in GitHub in this link, and in order to install it you can follow the README file. In our case you just need these 4 lines. Open your RStudio in a new project or in your current one. Okay, and then run it. In case that DevTools brings you trouble, it can happen sometimes with the Windows users, just go here, you can download it as zip and then you can build it locally. This package is based on 2 publications where our main 2 algorithms come from. It includes 17 functions. 4 are blocking functions, 3 pairwise comparison, 2 are labeling ones where our algorithm or skyex and skyex are included, and several for analysis and visualization. So let's go now to our package. You can find the package we just installed here. The name is skyex. If you click, you can see all the functions here that we use. And if you click in one of them, you can go and you see the arguments and how can you use it for more documentation. So we're going to use 3 datasets for the moment. 2. This one is entities. They are spatial entities in the region of North Denmark, extracted from Google Places, Foursquare, Yelp, and Crack. They contain the ID, the name, longitude and latitude, the categories, which means what type of business they are, and the address. The other dataset is restaurants. You can just call it data restaurants because it's already included in the package. And it contains the name, the address, the city, the phone, the type, what type of place it is, and the class. If the class is the same, for example 00 or 11, it means these 2 are the same entity and these 2 are the same entity. This dataset can also be downloaded from this link. It's this one, a collection of 864 restaurants. Okay, so let's first do some blocking. Blocking is used to group together those entities that are of interest to be compared pairwise. So we want to have some kind of similarity already. The most natural way to do blocking would be a Cartesian product, but that means a lot of computational power. We can do textual blocking, which means we group together those entities that have a high-text similarity regarding one of the columns. You give the dataset the column name that you want to perform textual similarity on. I'm giving here the method Jaro-Winkler with a maximal distance of 0.1. So in order to know which methods are allowed, you can go to the textual blocking and you see Levenstein, cosine, Jacquard, Jaro-Winkler, and QGround. For example, let's see Levenstein, let's be less flexible with 5. First, let's see how Jaro-Winkler performed. I'm just projecting these 2 columns, name.x and name.y, of the 2 different entities that got together. So it's quite good, but maybe we're being too restrictive. We're not allowing a lot of change, which means we could miss some good pairs. So now let's be super flexible and let's see what we got. Okay, so we're doing good here, but then we have Arts Delhi with Stage Delhi, which might not be the same thing, and a lot of pairs that actually might not be very good candidates, and we're gonna compare them. Anyway. As you notice, these functions, they output a data frame of pairs. So after you get them from the blocking, you can immediately perform the pairwise comparison. You don't have to form the pairs yourself. It's already output as a data frame of pairs. For the prefix blocking, we're going to group together those entities that start with the same characters. For example, for the prefix size of 4, let's see what we got. 21 club, and then Adriano's Ristorante with Adrienne, that maybe it's not a good match. Aquavit and Aqua here. We got 776 observations. Now let's try the suffix blocking and see what we get. We got 2,209, a lot more. And now we see what is actually the problem. There are a lot of words who finish with the word bar or restaurant. So we get together, for example, we get to compare monkey bar with oyster bar that maybe has nothing in common. Okay, so let's keep the textual blocking that we run with Levenstein and max distance of 5. It will have a lot of observations, 7,746, which is plenty, but let's keep that for the moment. Now for spatial blocking, we cannot run it on restaurants because we don't have longitude and latitude. But we're going to run it on the entities dataset where we have this kind of information. So let's run it, and we can even put a maximal distance of 30, which means 30 meters. This is a very user-friendly way to define the parameters of the function, because it's difficult for the user to know in degrees how far 2 points should be far from each other. But when you say 30 meters, it means I want to compare points that are at most 30 meters far. Okay, so we get plenty of entities here. As you see, we got H and M that got together with these other places that might have nothing in common, but they are just in the same street. The spatial blocking helps a lot when we're using spatial entities, because there could be changes in the way that the name is written, but from the fact that they are in the same point, we get already a lot of information and good candidates. Now let's perform pairwise comparison. Let's do a text similarity on the names of the entities with Levenstein and see what we got. Okay, so this one that is the same gets a 1. Arts Deli with Stage Deli 0.5, but closer with Brand's Deli, even though in the meaning maybe not, but they share more consonants. But then we get very low similarities to the names that they have nothing in common. So it's a promising similarity to separate the good candidates from the bad candidates. And now we can also try it on the similarity of the address. Let's try, for example, with Jacquard, because even the address was expressed as a string. Okay, and let's look at our comparison. So the first one is the same, it just changed one consonant, and this one had nothing in common. This is the same, looks good. Regarding the spatial similarity, let's perform this on the blocks of the entities that have the longitude and latitude. In this case, I'm going to need a maximal distance. I'm putting 30 to have the same as the blocking, but we need it because the values that we have in all the pairwise comparison module, they are normalized from 0 to 1. And for this spatial similarity, we need a threshold that beyond that, our entities are not similar for us, and this could be 30, for example. That's how we also can get normalized values. So let's check. Okay, so we see, for example, these that are the same point got a similarity of 1, and we have a low one here. Yeah, for 0 is the ones that are 30 meters far from each other. Okay. For the semantic similarity, it changes a bit. We are using Wu and Palmer similarity that comes from WordNet, is a metric. There exists a library, WordNet in R, but it does not have the metrics. The only way to do it is to implement the metrics, and to do so, we need the path of the words in WordNet, and this can be achieved through recursive functions, which through experimentation they show to be very time-consuming. So the best way to do it is, the way that we chose to do it is having Python scripts. The only thing you need to do is to have a Python interpreter or install one. In my case, for example, I have PyCharm. You create a project and you give the path in this Python path, and then you give the name of the method. In my case, I'm using UN Palmer, but it could be also another metric. Let's go with here. So we have path and UN Palmer. and we can calculate it with this metric. In the column, we give those column types that have that need to be compared semantically. For example, the word restaurant and food, if you compare it syntactically with Levenstein, for example, we're going to get a similarity of 0 or a very low one. But if we compare it semantically, we will going to get a high one, which is more intuitive because in the restaurants there is food that is being served. It takes a bit longer because it's 7,746 pairs, but it was just a couple of minutes. And let's see what we get. Okay, so American and steakhouses get 0.4, French and French bistro gets 1, Californian and American 0.94, which is very good, Californian and Mediterranean 0.3, acceptable. So these are very intuitive similarity scores. Now we can try a bit of the labeling. We can load some data that already comes with a package that is manually labeled pairs, 1,500 observations, with pre-calculated similarity of name, similarity of address, similarity of semantic, and their class. Okay, so how our labeling algorithms work, skyex F and skyex D, they actually rank all the pairs regarding the Pareto optimality rule in different skylines, regarding their similarities. You don't need to give any scores or any functions, weights for the similarity values. You just need to say if you want a high or a low value. So my preference is to have a high similarity of each of them, which would make sense. And then I can just call the skyex algorithm, which will try all the cutoffs and then choose the one with the best value of the F measure. So we give the data, the preference, and the column that contains the label, where the positive and negative class is, how it is shown, so with a 1 and a 0. So in the F object, we have the classes that you can immediately attach to your data. There is a data frame of analysis that with different levels, it shows you the precision, recall, F measure, but we will see it further in the analysis module. And it shows that it cut off at 90 skylines with an F measure of 0.845. Okay, if we don't have the labels, we can run the unsupervised version of it that will just take the similarities of the points and calculate the density function, and through the first derivative decides for a cutoff. Same way, it has the classes, the analysis, and fortunately for us, it cut in the optimal 90th skyline. And we can take the classes in the same way. Now let's check for our pairs from the restaurants dataset. First of all, let's put the class. If it's the same for X and Y, then put a 1, otherwise 0. And let's run both algorithms and put into respective objects. Okay, so let's see, we have them here. This one is from skyex F, that we got an F measure of 0.7, and it cut in the 7th skyline. But for this other one, for the unsupervised, we got on the 10th, so a bit further, and we don't know the F measure of this one. Okay, so we can attach it here. We can also, if we want, evaluate the different methods. For example, for the pairs manual, we can call evaluate function, evaluate skyex, where we need to give the prediction, and our prediction we can call it directly f.object classes, and then we need to give the labels. The labels is in our data class, and then the positive class, which is expressed as a 1, and we can get the value here. Okay, so precision, recall, and F measure. Okay, now let's perform some analysis and evaluation. First of all, let's plot the cutoffs and see. We can see that while we start with a low F measure and it grows until at the cutoff where we cut, and then it falls again. So we have selected the one with the best cutoff. We can decide to plot also the precision, which first it starts good with the points in the best skylines and then it drops. It's intuitive. And then the recall, of course, the more we explore, the better it gets. Or even plot all three metrics in one graph, like in this one here, that we can see how each of the metrics evolves while moving from one skyline to the next. Now let's plot the unsupervised version. We can see the first derivative here, and this is where we cut. The one when it, for the first time, becomes negative. And if you feel like this graph is too raw or too smooth, you can always play with the smoothing parameter. We used 5, you can use an 8 now, and you see how the cutoff is pushed a bit further. And the evaluation that I showed even earlier, that you can plot the values of precision, recall, and F measure. Okay, another way is also to plot the pairs, see their similarities, how they are, and what label they got. I'm going to plot 2D. It's more intuitive to use 3D for us because also we have the similarity of semantic, but let me just show how to use the 2D. So this is the graph we get. The true positives, true negatives, false positives, false negatives. We see we have a lot of false positives that we are labeling incorrectly, not as much as false negatives, so we get a feedback for our algorithm. Now let's plot 3D to have a better understanding, and this graph is more illuminative. Now we really see where the problem is. The false positives, they are, all of them, they are in points with a high similarity of semantics, which means that it's intuitive actually. Two pairs, if they are too similar in terms of semantics, it does not mean that they are the same one. For example, two restaurants, they might not be the same entity. So now we know that we should be a bit careful with the similarity of the semantics. We can also decide to plot it 3D, and in that case you get a more interactive view that you can move it around and see better each of the points and the observations. Okay. Now let's inspect a bit the results that we got from the restaurants dataset. Let's plot first their cutoff. Since here we see that something is not very good. We get an F measure in the beginning that is good, and then it drops, and it drops very fast, which means when we move in these skylines, we are not getting anything worth it. Let's just plot all the metrics and see what's happening. Look at the precision. It drops very low, which means that we are actually, if we move here, we would be labeling positives, stuff that they are not positive. Our precision will really fall. So maybe our blocks were very flexible. If you remember, we used Levenstein of 5. We have 7,746. So we are moving to different skylines and we are not discovering anything important. Let's check for our unsupervised version. It cuts at 10, and even if we decide to smooth it further, it still stays in the same cutoff, which means it's a very deep change there between classes that indicates that here is where we should cut. Now let's plot 2D. The pattern here is different from the other one. We have a lot of values for the similarity of the address here, and we see we're making mistakes from false positives and false negatives. If you remember, our F measure was 0.7, so not very good. Let's now plot 3D. Now we see our blocks contained a lot of true negatives. Look at all this clutter here that we have compared. So maybe we should have been more restrictive with the blocks. You can also change the colors of the graphs. If you don't like this blue, you can say the color of true negatives, for example. I want to have it as yellow. And you can get another color or move the legend. For example, legend.x 0.65 to push it a bit further. Okay. You can also plot the interactive plot the same way, and you can get different views of this data set from different corners. So we are feeling that our blocking wasn't the best here. We want to do a bit better. The only way to actually check it is to calculate the Cartesian ground truth, have all the comparisons, and see with our blocking how much of the positives we miss. Because that's the thing we care about. We don't want to miss any positives with our blocking techniques. So to calculate the ground truth for this data, you can just use the textual blocking, for example, and with no restrictions. So you call Jacquard with maximal distance of 1, which means even pairs with Jacquard distance of 0 will be together, will be listed as pairs. We're going to get a big table here that has the Cartesian product. Let's wait for it. Yeah. So a huge table. And then let's put the class to it. Perfect. And now we can call our function that gives you a number from 0 to 1 that shows the positives that occupy a part in our blocks. A high value, it means we're doing a good job. So we get 0.78, which is very good. But we get this number with all these comparisons and look at all of this clutter. What if we had been very restrictive? Let's go back. Let's go back here now where we said 5 and let's put 2. Let's be more restrictive. Okay, note here. From 7,746 we got 147. Wow. We should have missed now plenty of positives. Let's calculate how much we missed. Very surprising. Just 0.75 the change, so 0.03. It's really worth having these blocks, which are a tiny portion of the other ones, and have a lot more positives. They are more efficient. And definitely the labeling will work better. Let's do the labeling now from beginning. So let's calculate. Let's put the similarity of the name as we had it before, similarity of the address, semantic similarity. Remember here we took long to run it. Now it's going to take just some seconds. Yeah, because it's a very tiny portion of the data. Okay, so now we're here. Let's put the class and then call the labeling algorithm. And look at the result. An F measure of 0.958, which is a very good improvement. And let's even plot this data. Look how little we have now of clutter. So actually this change, this feedback that we got from the analysis and visualization module, it helps us redefine our blocks, find good values for the labeling algorithm, and go back and with just minimal changes you can run again the procedure and find the best representation of your model. So I hope you enjoyed this video. Feel free to download the code from GitHub, to contribute to it, to leave your comments, and thank you for your attention.